Hello, good people. Welcome to the last example of the Lagrange error. And I will say this from now on, any practice that we do with the Lagrange error is going to come in the form of an actual released free response question that would include something like this. So, this is an AP style Lagrange error problem. Notice that as we do this, it's not going to require as much as example 3 or as example 2 or even maybe, well, kind of like example 1 because we don't have time. We don't have time to do all the work that we did with example 2 and 3. On the AP exam, you'll be given enough information to actually figure out the Lagrange error bound uh, with some ease. So let's read what we have. The function g has derivatives of all orders for all real numbers of x. Let t sub n of x be the third degree Taylor polynomial for g about x equals 1. So right now, I already know a couple of things. This is a third degree polynomial, so n equals 3. I also know my center, my c, my center is 1. Let's continue reading. The maximum values of the nth derivative of g for x's between 1 and 1.7, including 1 and including 1.7, for selected values of n are shown in the table. So I'm looking at the table, and they're saying if I want to find the second derivative, the maximum value of the second derivative of g at an x value that's between 1 and 1.7, including 1 and 1.7, is 5.1. If I'm taking the third derivative, then I know that the maximum value for the third derivative of g at any x value between 1 and 1.7 is 1.9, and then the same thing with the last line. What is the maximum error guaranteed by the Lagrange error bound when t sub n of x is used to approximate g of 1.7? So I don't need to write out the polynomial. I don't need to worry about what the answer is. The question is about the error. And remember that the error is the remainder. So we have this formula that says to figure out the remainder, and we're going to figure out the remainder for the third degree polynomial. And we're going to find the remainder or the error for x value 1.7. That has to be less than or equal to the maximum of f prime. Now, which prime? Well, the n plus 1 prime, but n was 3. So then I'm looking for the fourth derivative at some z value divided by n plus 1 factorial. Well, that would be 3 plus 1 factorial. Well, that's just 4. 4 factorial times x minus c, and I know my x value, and I know my c value, to the n plus 1 factorial. Well, if n is 3, n plus 1 is 4. This is what the formula says. And if this is what the formula says, and I can find the maximum value of the fourth derivative at any z value between 1 and 1.7, well then that would be 3.7. So this thing is less than or equal to the absolute value. The maximum value it could be is 3.7 times, if you subtract this, I get 0.7 to the fourth, divided by 4 factorial, which is 4 times 3 times 2 times 1, that's 24. And if I can figure this out, then I'm in business. Well, you have a calculator. I have a calculator. We have a calculator. So let's figure it out. I go to my calculator and let me clear some stuff and we're going to type it in. 3.7. Oh, I forgot the point. 3.7. Now I have too many threes. Times 0.7 to the power of 4 divided by 4 factorial, which is 24. If you want to put the factorial there, that's fine. If you want to write 4 factorial on the calculator, that's fine. I just did it in my head. 4 times 3 times 2 times 1. Press enter, and here is our maximum error. 0.0370. I'm going to put 4 decimal places just to make sure. Actually, I guess it really doesn't matter because the last decimal was 0.03, no, 037. If I put the last 0, and I round it to the fourth decimal place, yeah, it's still going to be 0. So I think I'm okay. I can put this, I guess, and make it a little bit more accurate to up to 4 decimal places, but this is the maximum error. So my remainder, my error has to be less than or equal to that value. And I figured that value because I was given just enough information to figure it out. But it all comes down to this formula. That wasn't really that difficult. And if you know where everything goes, it's a pretty easy way to gain points on the AP Calculus exam.